Hello and welcome to Lambda School Data Science, Unit 2, Sprint 3, Module 1. We're going to talk about logistic regression today. Logistic regression is the first of several models that we're covering in a sprint that we call advanced regression. If you think a little bit about the meaning of the word regression outside of a statistical context, that sentence might seem a little bit funny to you, and that's okay. What we really mean is you've now spent a few weeks learning in depth about linear algebra and linear regression. That is the foundation of an awful lot of predictive statistics and modeling, but there's a whole lot of other techniques out there, just like there's a whole zoo of probability distributions. And just like with that zoo, we want to show you some of the greatest hits. There's way more out there than we're showing you, and what we're showing you we will not go into as much depth mathematically as we did with linear regression. Our goal is to give you useful tools, show you how to use them, give you some intuition for them, and really when to use them and when not to use them. That's often the more important part. So with that, logistic regression. What is logistic regression? Well, logistic regression is a true workhorse, and this is also a true workhorse. This is actually, as you might be able to tell from the uniforms, this is a military picture, and military pictures are in the public domain, courtesy of our government. This horse is being checked out for his health, but presumably this horse does something productive for the United States military, and logistic regression will be a workhorse model that you will go to time and time again, a great baseline in particular for classification, but we will discuss it in the coming slides. First, though, let's think back to what linear regression is, what you can explain with it, right? When do you want a real number, right? If you're predicting something like income, age, then it makes sense to say, well, that's basically a real number, basically a continuous value. Again, the true theoretical mathematicians might take issue with that. Income is discretized down to the penny, say. And also both of these examples are non-negative, right? But they have no, at least, inherent ceiling, no specific number that we can point to and say it can't be any higher than that. So it goes along some continuum. Pause for a second and try to come up with your own example of something like this, that linear regression is good for predicting. And also maybe think a little bit about what situations are there where linear regression might not be such a good approach, might not be appropriate or able to model the value you wish to predict. Again, pause, think. Did you pause? Did you come up with your own examples? I hope so. You're also welcome to bring them to class for discussion, of course. What is the case that we want to use for logistic regression? Well, really it's about restricted output, and that might seem like a strange way to put it. Why would we want to restrict or limit what a model can do? Well, a clear situation is binary variables. If you want to predict sick versus healthy, or gender, from the two traditional gender categories, then you might want a model that limits its output to those things. It doesn't make sense necessarily to give continuous predictions in these situations. These are classification problems. There's other cases that might be a little bit less obvious. What about approval rating? This visualization is the approval rating of President Nixon, and the green is approve, the red is disapprove, the yellow is indifferent, and it's over time, and we don't need to go into the history of the 70s in depth, but certainly Nixon's career did not end on a high note, and we can see that in this plot. Now you might think, well, these numbers, they're values, right? Approval rating it ranges from around, about as low as 20 up to almost 70, right? And the other values have ranges themselves similar to that. But that's a little misleading because, well, these are percentages, right? And so think, what is a percentage really? It's not a number. I know that might be how people like reporting it, but it's actually a proportion, something that lives in the unit interval. So we're really just saying, something from about 0.2 to 0.7 or something like that, right? And because it lives in that unit interval, you can actually think of it as a binary variable, just one that has some range that's restricted. So you could fit a linear regression, right? You could try to have a linear model, and you could extrapolate what Nixon's approval ratings are likely to be based on that. But if you do that, you might conclude that at some point in the future, he's destined to have below zero support because there's a pretty, there's a down tick in this red line here. And if you extrapolate whatever events or data covariates you wish to correlate with it and say, well, if this keeps going this way, pretty soon he's going to have negative 10% approval, that's not a great thing. That's clearly an absurd prediction. So linear model does not work in these situations. Thankfully, there is a better way. This is our friend here, the sigmoid logistic function. And I refer to this as squishification. To be clear, squishification, if it's not obvious, is not a technical term, but it captures the intuition well for what's going on here. So what is going on here? Well, the problem with modeling Nixon's approval with a linear regression is that a linear regression, if you feed it the right coefficients, can output anything along the real number line. And that is not where we want approval ratings to live. Approval ratings are proportions, are percentages, are essentially classification, even if it doesn't necessarily seem that way to you. And so all of that class is best modeled with something like logistic regression, because logistic regression takes this function here, this sigmoid function, and uses it to squishify, to map values from the real continuum to the unit interval. So you can see the x-axis actually goes from negative infinity to positive infinity. It asymptotes out, just like a lot of continuous probability distributions and CDFs do, but it does go along the entire range. And in the y-axis, it ranges from 0 to 1. In fact, it is a CDF. Think about that, right? It is a cumulative distribution function. Any cumulative distribution function can have this property, can map numbers from the real line to the unit interval. The sigmoid one here, the logistic function, is a nice one to use. It's called sigmoid because it looks like an S, and it's nice and smooth, and for calculus reasons that we will not go into, but mostly having to do with the fact that e to the x's derivative is still e to the x, it has a lot of nice behaviors that make it a convenient choice for a wide range of situations. So what does this mean? Well, this means that our coefficients at the end and the predictions we output at the end of a logistic regression are not going to have a straightforward linear interpretation. They have to be passed through the logistic function in order to be mapped to a probability. And then for classification, you'll typically pick a threshold, say 0.5, and if you are above that, you classify it as a 1, and if you are below that, you classify it as a 0. But there are some situations, like approval rating, where you might actually not, essentially round it like that, but instead report the actual value. Either way, you're limiting the full output range to something that lives in the unit interval. The logistic function also, of course, has to be used in the training of a logistic regression. That's not a detail that we will go into, but I encourage you to explore it if you're curious. Essentially, it has to transform the values being targeted, so we make sure that we optimize the errors appropriate for this. And again, as I alluded to earlier, this is just one particularly useful function. There are other functions that you can do to have this, and these are called link functions. Probit is another major example. Probit is related to the normal distribution, stands for probability unit. So, bringing it all together, this is essentially what I was just saying, but stare at this for a second and let it absorb. Squishification just means we're using a link function, which is essentially like a CDF, in our case, the logistic sigmoid, mapping real values to the unit interval. This means that we're fitting a regression that, at its heart, actually, is still linear. And that's the perhaps somewhat strange thing to think through here, and it's totally okay if you don't get this all at once. We will be going over this again in the notebook and in class. But a lot of the underlying math and the way it actually works and the way you interact with the model is still very much like a linear regression. That's why we taught that one first. But there's this non-linear boundary and restriction on the output. We don't want to allow any output, and so we squishify it. Again, non-technical, but I think intuitive. And what does this let us do? Well, it lets us model probabilities, like approval rating. It lets us model binary values, 0, 1s, and you can actually even model general multinomial classification problems by using a whole collection of logistic regressions all together, giving the probability differences of being in these different classes and then outputting whichever class is the most likely. We will also look at that in class. If it sounds confusing, that's because it kind of is. There's a lot of coefficients, but just predicting is actually not that bad with it, and scikit-learn in particular makes it actually a pretty nice experience. So, thank you for watching, and as always, here are some sources of those images, our military horse and Nixon's approval rating and the logistic curve function. Thank you.